Okay, come, let's start for today. Right, so these two are the answers for last lesson. I just want to give a bit more idea behind these two questions, right? Okay, before we move on to today's chapter on intermolecular forces. All right, so last lesson I discussed the idea of intermediate bonds. Okay, so as you copy, just listen up a bit. It's a mixture of both ionic and covalent character. Okay, so it's a mixture of both compounds, both ionic and covalent properties, right? So we have acknowledged two different factors. The first question, right, is to compare the cation's charge density. So it's a little bit longer. Okay, I will later highlight all the keywords. Okay, right now I'll just look at the broader idea first. We clearly are comparing the cations, so it's the charge density that's affecting this question. The second question is about I minus and F minus. So we are more looking towards the anions radius. Okay, we discussed these two factors the last lesson. I talked about how it works. I'm not going to talk about how it works again, okay, because I'll move on very quickly. Okay, but we are mostly looking at the keywords in your writing. Okay, so to keep the answer as concise as possible, the first portion here is to discuss charge density. Okay, again, you must acknowledge the charge first and then the ionic radius. Because remember, charge over radius, we've reiterated this point many times now. Okay, you need to talk about both factors before we can come to a conclusion. Afterwards, okay, the rest of the keywords I already discussed last lesson. You just need to apply it in this context. What does it polarize? Just make sure you're polarizing the electron cloud of Cl minus. You don't just say polarize Cl minus. Only the electron cloud can be polarized. Okay, today we'll be talking more about what an electron cloud actually is. Okay, then you can just conclude with more covalent character. And if you are more covalent, that means you are more or less ionic. More covalent means less ionic. It's kind of like a mixture of both. You can think of it this way, guys. If you are looking at MgCl2 and NaCl, I love to think of it as a line diagram. MgCl2 and NaCl both have the same length if you think in terms of this line, but MgCl2 has more covalent as compared to NaCl, a lot less covalent character. In other words, the rest of it is ionic, as you can see over here. So just by looking at the covalent character alone, you can see MgCl2 is more covalent than NaCl. And in other words, that means you sacrifice more ionic character in that sense. So it's always a mixture. It's a blend of both. The second question talks about the anion. And we talked about it last lesson. Anion must look at the ionic radius. Because the anion is the one getting polarized. So here, if we draw the same exact line diagram, you can get the same exact answer. Okay, so let me just borrow the first diagram. This is the same thing. AgI has more covalent character than AgF. In other words, AgI deviates more from the ionic model. Okay, the question talks about a few keywords like ionic model and all that. Last lesson, I already broke it down for you guys. Okay, what all those terms mean. So I'm not going to repeat myself there. So far, any questions? Okay, this is one possible way you can visualize this in your head. Everything is a mixture of both. It's just what proportion. Maybe this is 60-40, this one is 90-10, something like that. Okay, so far. And once finish copying all these things, okay, if you have any questions, please feel free to ask. The second answer, as you can see, is much shorter because the moment you talk about ionic radius, you can jump straight to how easily polarized it is, and then you can talk about covalent character next. Much easier way to explain the second part because you don't need to justify ionic radius, but you do need to justify your charge density. So a little bit more demanding on the first question. Okay, so far. Can Right. Okay, so once we are done copying with all this, I want to quickly move on to intermolecular forces. That's our main focus for today. And I would say that this is the most important part of chem modeling. All right. Have you finished both concepts in school already? Not yet. Oh, like, is it going to finish or like halfway through-ish? Like, still going through, right? Okay. Okay. Have they released lectures for like the next chapter already? Because I just want to measure like what's your pace. So the next chapter is redox. So they split both. Okay. Oh, that's good. Usually schools like to combine them together. So they call it one topic. Then they just release lectures for everything. Okay, that's good. Okay, so far any questions for this? Okay, generally, guys, last comment. This is not difficult to score in exam because this is legit just how they test. It's very content-based, it's less application-based. Meaning to say, in exam, right? Okay, even though this concept may be a little bit hard to digest in the first place, it is not difficult to gain the marks over here. There are some other concepts, right, which are very easy to understand, but very hard to score in exam because of the application questions they can come up with. So try to make sure you study this portion. The moment you study already, I can say very simple, you can score for this kind of question. Anyways, let's come to intermolecular forces. Okay, I'm going to call it IMFA for short from now on. It's a little bit easier for me, for everyone, in fact. Okay, now I want you guys to know what's the broader idea of this topic. Okay, why are we studying chem modeling? The reason why we are studying chem modeling is mainly due to intermolecular forces. And the reason for that is because intermolecular forces allow us to explore physical properties. It allows us to explain whatever we see in real life. Okay, basically, right, what are some examples of physical properties? Any idea? Any example? Okay, good. Okay, boiling points, melting points. Essentially, right, guys, it allows us to explain why water has a relatively low boiling point, whereas why like certain compounds have a super high melting point, right? All these things that we observe in real life, we try to find an explanation for it, and it's all because of intermolecular forces. Okay. On the other hand, it also allows us to explain solubility. In fact, these are the two things that we seek to explain by the end of this segment, by the end of this topic, basically. Okay. Now, why is this so important? Because, right, there is one thing that a lot of you guys tend to confuse with. What exactly are intermolecular forces? Perhaps you all remember van der Waals. Okay, these terms we're going to have a little bit of a change in name in this chapter today. Okay, but anyways, let's take a look at the carbon dioxide molecule. This carbon dioxide molecule has an outline around it. Okay, you guys might want to guess, right, what this outline represents. Okay, but of course, there are not just one carbon dioxide molecule. There's multiple, there are millions of carbon dioxide molecules interacting with each other. When we refer to intermolecular forces, inter means what? Inter. Between molecules, right? So intermolecular forces are basically these attractions that exist between the molecules. Why is this so important? It's because, right, I do not want you all to think of this as covalent bonds. Now, the moment you mention the word covalent bonds in your answer, it is wrong. A lot of people tend to conflate these two concepts together. Now, I'll give you an example in a bit, okay? But before that, you want to make a guess what this circle represents? Good, okay, this circle represents, or this outline, to be more specific, represents an electron cloud. What is an electron cloud? Okay, it's very simply the region around the molecule which contains all the electrons. So basically, within this boundary, you can find all the electrons of carbon dioxide, for example. Okay. Now, I can give you guys more examples here. Other than carbon dioxide, we have learned how to draw a water molecule. So this is a water molecule. This is another water molecule, correct? And they have their own intermolecular forces of attractions. Guys, when I boil water from liquid to gas, am I breaking the covalent bonds or am I breaking the intermolecular forces? Good. Okay, be very careful here. When I boil water, when you get boiling point, basically, it's all about breaking of intermolecular forces. I am not breaking the covalent bonds. I'm not destroying water molecule. I am basically, when I turn liquid into gas, right? Okay, the interactions are broken, they are further apart, and that's exactly what gas is, right? Gas is where the molecules are very far apart from each other. So from now on, right, be very clear. Intermolecular forces is the thing that is responsible for all these things, like boiling points, melting points, so on and so forth. Okay, never covalent bonds. Okay, I want you to take down more things. Intermolecular forces are generally weak and easy to overcome. On the other hand, covalent bonds from now on, you all must acknowledge that they are very strong. They're very strong, which means you can't break them when you, like, let's say, heat it above this boiling point. That is not how it works. So our concern in today's lesson is not about covalent bonds, it's solely on intermolecular forces. So this is what a wrong answer will be like. What happens when you boil water? Okay, I break its covalent bonds. Okay, please never tell me that ever again. Okay, this is a very important idea. And how does this translate into your questions? Okay, I may have mentioned this last time, but let's talk about it one more time here. Fundamentally, we learn structure and bonding, right? Now, our focus in today's lesson is mostly on simple molecules. Okay, so let's write this down. Simple molecular structures. So let's zoom in into a very specific part of classes of compounds. We are looking at simple molecules. And guys, because simple molecules are usually what we discuss for intermolecular forces, I want you guys to take note. When it comes to bonding, what should I write? I'll give you guys a bit more examples here. Okay, follow me on this. If you have an ionic compound, what's the structure called? Oh wait, ionic compound. Ionic compound would be like giant ionic structure, right? Okay, then what is the bonding called? Ionic bonds. Okay, very simple. Metals, giant metallic lattice, the bonding is called metallic bonds. Very simple, right? Okay, but simple molecular structure, you should never tell me covalent bonds. We are not interested in covalent bonds because once again, guys, the physical properties are explained using the intermolecular forces of attractions. So even though they ask you for bonding, we are more interested in the IMFA. So today we're going to learn the different types of IMFA, and this is what you should be specifying in your answer when they ask for structure and bonding of a simple molecule. Make sure this is written out. Okay, this is very important. Okay, so far? All right, okay, so get an idea. So the box at the bottom of the page, they're asking what's the difference between covalent bonds and IMFA. That's basically what I discussed here. Okay, so you can just put an arrow there. Okay, there's no like written explanation. Okay, it's a combination of both. So any questions so far? Okay, go ahead. All right, okay, if you don't have, right, we're going to proceed over to the first type of intermolecular force. So let's remove a few of these things first. Now, last time you guys have learned this thing called van der Waals force. We're not going to use that term already. Okay. The first intermolecular force, I need you all to write down the full name because the notes never print down the full name yet. Okay, so I'm going to write this down also. Instantaneous dipole, induced dipole attractions. So it's also known as IDID attractions. Okay, very long, a very long title. Now in the exam, you are allowed to just use the short form, IDID attractions. In fact, I don't think it's really a must to write down the full name. But it is important for us to understand how this name even comes about. Now last time during my time, right, I just accepted the name without actually understanding what it is. Okay, and your school might do the same thing by just skipping past it. Okay, but I think it's very important. You see the box on page 42? Is it 42? Yeah, okay. It asks you what is the origin of the IDID attractions. Okay, some facts first, guys. IDID is the weakest interaction we're going to learn for now. Later, I'll tell you more stronger interactions. And at the same time, the second bullet point says, right, it exists in non-polar molecules. Okay, we'll recap a little bit of non-polar molecules. But this one, right, I need you all to write a little disclaimer at the side. Very important. Yes, it exists in non-polar molecules. This statement is not wrong. But at the side, please write this down. All simple molecules minimally have IDID attractions. You can think of it as this way, guys. IDID attractions are literally the building block of simple molecules. It is the fundamental interaction that all simple molecules must have. Yes, there are other types that we're going to learn later. Those exist for other types of molecules as well. So let me clarify this one more time, guys. Non-polar molecules only have IDID attractions. Later I'll come back to it. How about polar molecules? Probably have more stuff. Okay? So this is very important to acknowledge. This is how your school will acknowledge you guys also. I'll just give you guys a heads up first. So what does it mean by IDID attractions? Okay, first of all, guys, what is a non-polar molecule? Can you all remember what it means? What does it mean to be a non-polar molecule? Okay, so we talked about the idea of electronegativity last lesson, dipole moments the last lesson. So if you have a non-polar molecule, is there an overall dipole? No. So there is no overall dipole, possibly due to a couple of reasons. Maybe it doesn't have any polar bonds in the first place. For example, you could be like CH4. Guys, is CH bond polar? No, okay, CH bond is not polar. That's the one exception I want you guys to remember. On the other hand, you also have something like carbon dioxide. I drew carbon dioxide just now. Does carbon dioxide have a polar bond? Yes, however, however, because of the linear shape, right, the dipoles cancel each other out in opposite directions. It could be any one of these scenarios. Okay, that's just a representative of each scenario. Okay, it doesn't really matter here. What matters is if there's no overall dipole, are the electrons going like favored towards any side of the molecule? You think of electronegativity. If there's no overall dipole, are the electrons concentrated towards any particular side? No, right? So I want you to think of this. For a non-polar molecule, I want you to think of its electron cloud. Do you all think the electron cloud is evenly distributed or unevenly distributed? Evenly, good. Electron cloud of a non-polar molecule is evenly distributed. Okay, go and highlight these two keywords. We're going to use a simpler keyword in a bit. Okay, last lesson we used the word polarized. We're going to come back to that later. But for now, I need you all to imagine which one do you all think an electron cloud should look like if it is evenly distributed? Which one looks evenly distributed to you guys? The left one, right? The right one, right? Oh, what the hell is this? Okay, this, right, is the electrons gravitating towards one side. Perhaps it's because this side has a more electronegative atom. That could be a reason. I'll come back to that later. But for now, right, this fact here is very important for us to understand the origin of ID-ID attractions. So let's come to this. Okay, guys, think of it this way. I'm going to draw a diagram. I want you all to draw this diagram in your box as well. Think of two non-polar molecules. Okay, the electron cloud is very nice, very evenly distributed. Do you think there can be any interactions existing? First of all, guys, are there any charges over there? Are there any like partial charges or anything? Nothing, right? So if there are no partial charges, there can't be any interactions between the two molecules. However, guys, okay, let me give you a question. Electrons, are they always moving or are they stationary? No, actually not. Okay, electrons are, guys, for a fact, right, electrons are always moving. They're never stationary in a single area. Okay, because they're so small, okay, they can just move around. So, guys, at any random moment in time, right, the electrons, because they are just moving all about, they could just anytime move towards one area, one side of the molecule. So what this happens guys, if there are more electrons on the right-hand side, should it have a negative or positive charge? Wait, the right-hand side, a lot of electrons, there's a lot of negative charges, right? So there should be a negative charge here. But could it be an actual negative charge? Is there any ionic compound, any ionic properties here? No, right? Okay, we are discussing simple molecules, so it should be what kind of negative charge? Did we learn another type of negative charge? What is it called? Partial negative, right? Okay, a partial negative just means there's no actual transfer of electrons. It's just gravitating towards one side of the molecule. Whereas the left-hand side has less electrons, right? So what's this? Partial? Positive. Okay, so this happens, right, because electrons are always moving about, right, randomly. So what at any random moment in time, it's just going to sway towards one side. This right here is your instantaneous dipole. So I need you all to write this down. What is the meaning of instantaneous? Any guesses? You make a, okay, we don't have to use official terms here. Instantaneous means what? Okay, it happens in that instant, right? In other words, guys, this dipole was created on the spot. Okay, now these are simple terms that we are not going to use in our explanations. Okay, but they are created on the spot. It happened in an instant. In other words, guys, 1 second ago, it was perfectly distributed. And the next moment, right, because electrons are hyperactive, it's just going to be unevenly distributed. This guy right here is your instantaneous dipole. That's the first part of our explanation. Can you see this so far? Okay, later I'll write down the full explanation. Right now, I just need you all to understand first. So I draw all these diagrams. Then how about the other guy on the right? Okay, you all notice this. The other guy on the right, okay, initially he was evenly distributed, but the moment the right-hand side here, right, has a lot of electrons, how would this guy respond? Imagine this, you are here. There's a crowd of people coming towards you. What will you do? Will you go towards the crowd? No, right? You will also try to leave the crowd because no one likes crowds. It's the same idea for electrons. Why do electrons want to leave? Because they will repel. The idea is that when it's too close, right, this guy, the electrons will also repel towards the right-hand side. In other words, the guy on the right will also have a dipole because the electrons on the left are just going to gravitate towards the right-hand side. And this second guy is basically your induced dipole. What's the meaning of induce? I induce you to follow me to the library. What does that mean? Okay, I know it's not the correct word, right? Okay, but it's more like to influence, to cause something to happen. Induce, right, is to cause a dipole to form. More specifically in a molecule beside it. So it's kind of like a chain reaction, right, guys? In reality, it's not just two molecules, there's a billion molecules. So the moment this guy happens, the other guy there, the one on the right, it will also have another dipole. Everyone will now have a dipole. And that's how everyone has interactions. Can you all see this? The partial negative and partial positive will attract each other, and these are your ID attractions. ID. Now I'll go through this very, very detailed because I need you all to really understand how this comes about. Okay? Now, I'm going to write down the explanation, but this will make a bit more sense. So the first bullet point is this. Okay? It all starts because electrons are always moving. Okay? As electrons are always moving, the electron cloud of a molecule, or non-polar molecule to be specific, will be polarized at any point in time. Okay, let me pause here for a moment. I need you all to soak in this explanation and look at the choice of words that I've used. Yes, electrons are always moving about. And the key word here is electron gets polarized. We will not use the word evenly distributed because it's very long. I need you all to understand polarized means okay, to make it uneven. It's a verb, right? Okay, to make this uneven. That's what I mean over here. I also use the word at any point in time because that's the idea of instantaneous. It happens on the spot. Okay, you don't know when it happens, it just happens at any time. So it's to convey the idea of instantaneous. So the next couple of points is very simple already. You can summarize this by saying, this is an instantaneous dipole. And this instantaneous dipole will basically cause a chain reaction to happen. It will induce other dipoles to form. Which will induce a dipole in a neighboring molecule. Once again, pay attention to the choice of words over here. To induce something, it means it has to be for someone else, right? So that's why I use the word neighboring molecule. And I just use the word induce here, so it's quite an easy way of explaining this. In other words, guys, please look at the keywords that I've underlined. You must do the same thing as well. Underline the appropriate keywords. Okay, so let me summarize it in like one sentence. At first, it's nothing. Then 1 second later, right? The electrons move too much to one side, and then now everyone has the same dipole. That's how they all attract each other. That's literally it. Okay, so you summarize it in your head like that, and then you look into the details. Sometimes, once you understand how it works, the details you don't need to be very hardcore memorized with. Okay, you will understand how to come up with the explanation yourself. Any issues so far? Okay, Ken? Right, so that's how ID attractions come about. Now, as like everything else, I want to look at the factors affecting its strength. Okay, first of all, any last questions? Okay, now how do we look at the strength? Okay, so this one, let's pay attention to this. Okay, quite important. Okay, of course, right, guys, different non-polar molecules will definitely have different ID strength. Maybe some are stronger than others. So what is the factor over here? when we look at factors, okay, for IDID, the number one factor, right, is the most important one. I'll explain this in a bit. Okay, is the size of the electron cloud. Meaning to say, when you compare two molecules, you must look at the size. First question you have in your head, how? How do we compare size? I need you all to compare the MR of the molecule. Everyone knows how to compute MR. Just look at your periodic table and compute, right? I'm going to give you guys a simple example. Just write down this example first. If you have hydrogen gas versus carbon dioxide, can someone tell me who has the larger electron cloud? Okay, it's very obviously carbon dioxide, right? Why? Okay, the MR of carbon dioxide is like, you can go and compute yourself, 44. Hydrogen is a mere 2. Okay, so it's very clear that carbon dioxide is bigger, right? So what? That's the issue. So what? Guys, if you have a larger electron cloud, what does that mean? Imagine this, guys. If the electrons are larger, that means it is further or closer from the nucleus. Further from the nucleus. Okay, we follow the train of thought. If you are further from the nucleus, it means what? Okay, we kind of covered this in the last lesson, right? If you are further from nucleus, it means you are less attracted to the nucleus. That means you are more easily, what's the keyword for it? More easily. Okay, remember, I started off like that and then it became like that. What is the thing that happened? Polarized. Okay, this action over here from nice to not nice, right? Okay, it's not polarized. Okay, so it's more easily polarized. Now let me tell you guys what is necessary in your keywords. Your keywords just need to tell me larger electron cloud makes it more easily polarized. You can skip the point in the middle because that point is just for you to understand. You can write it down first. Eventually, when you understand already, you can pretty much ignore that part. So once again, I'm going to write down the keywords in your answer. You have a larger electron cloud. You must mention it is more easily polarized. Guys, if your electron cloud is more easily polarized, that means what? Are you bound to have stronger IDID attractions or weaker? Okay. If you're more easily going to form charges, that means the attractions are going to be stronger actually. Okay, so you think about it this way. I have a very small molecule versus a very large molecule. A larger molecule will form a it will polarize very easily. So that means the charge here is very big. You can see that. Whereas a small molecule can polarize a bit only. Okay, the charge is very small. So if the charge is very small, the interactions are going to be weak. If the charge super big, the interactions are going to be very strong. So that's the idea. If you're more easily polarized, you're bound to form stronger IDID attractions. And this will allow us to explain some of the physical properties that I've mentioned above. Later, we see how this can be linked to your physical properties. Okay, so far? Alright, okay, so this is the mental image you should have in your head, the picture you have. Right? More easily polarized, you're bound to form attractions more easily as well. Okay, which definitely will be stronger. And so far? Alright? Now, the reason why I want you guys to start this, right, is because I need you all to look at a disclaimer that I have. Okay? In what situation can you not compare the size of two molecules? If the MR is what? The same or similar, right? Okay, so guys, this is the thing that I need to mention. You must always compare electron cloud size first. Okay, that is like the first course of action when they give you two molecules to compare. Electron cloud size is basically the primary factor to compare. But of course, there are exceptions. If the electron cloud size is similar or the same, sometimes it's the same as well. Okay, then we will look at other factors. Okay, you may be asking yourself what the other factors are, which we'll go over in a bit. But I'm going to leave this here for the rest of the lesson, basically. Because no matter what, this rule will apply no matter what kind of interactions I'm talking about. ID, or whatever that's coming. Okay? Okay, we have a total of 3 interactions. It's just going to get stronger and stronger. We start off with the weakest one. Okay, no matter what, you must always compare electron cloud size first. Okay, because guys, fundamentally, all interactions have what? All molecules have what? All simple molecules have what kind of interactions? ID interactions. Can see that? And because all molecules have this basic interaction, you must always compare electron cloud size first. Okay, later we'll see what the questions talk about. Okay, so we'll look at another scenario. If you turn over to the next page, okay, we have another factor. Other than size, okay guys, if you can't compare size, let me give you guys a different scenario. Let's compare the surface area of the electron cloud. So in what scenario would that be the same size? Okay, basically the same MR, correct? How does this work? Okay, let me give you guys an organic molecule, C4H10. Now, how will you arrange the 4 carbons? Can someone possibly tell me? Any suggestions to arrange the 4 carbons? Okay, it can be very basic and arrange the 4 carbons in a straight line, right? And everything else is all hydrogens. Okay, we can ignore that. Okay, is there another way to arrange these 4 carbons? In a box, okay, correct also. Okay, but let's look at a more simple manner. Okay, box is correct lah. Okay, but we look at another simpler scenario. Instead of just arranging 4 in a straight line, we can also do what? Okay, we can put one C, right, in the middle. So we basically put 3 in a straight line and then one C in the middle, correct? So what I'm trying to say over here is that, guys, if let's say you're given these 2 molecules, can you compare the size of this electron cloud? What's the MR of these molecules? Both of them are C4H10, so the MR is bound to be the same. We can't compare the size, so we can only turn to surface area. Now, this is a good example, but not good enough to help you all see what's happening. I want you all to imagine this scenario. I'm going to make the molecule bigger. Imagine, right, I have a total of 8 carbons in a straight line. Now, let's say you have 1 drop. These 8 carbons, you think of it as 8 pieces of Lego. Very, very big Lego pieces. Now, I want to try to bring these 8 pieces, right, through a door. But the door, right, obviously it can't fit through like what, right? Okay, so it's very small. Now, assuming you turn vertically, you also cannot fit through the vertical part of the door, right? How are we supposed to bring this through the door? We have to make it more compact, right? Because this is it's too long already. Is there a way to make it more compact? How can we make this more compact? Okay, you can fold it or whatever. Okay, but remember the idea that I went through just now. Okay, instead of putting everything in a straight line, I can take some of the carbons at the end and put it where? In between, right? So I can show you guys the most compact way that I can make this long straight line is like that. I put only 4 carbons in a straight line. 5, 6, 7, 8. Can you see, guys? I have made this a lot more compact. I am bringing the same 8 carbons through the door, but now I can actually fit it through the door because it's a lot more compact, right? Now, based on whatever I just discussed, which one has a larger surface area? Which one occupies more space, basically? Okay, I couldn't bring this guy through the door, right? But I could bring this through the door because it's more compact. So, which one has a larger surface area? The left one. Yes. Okay, so I want you to think of it as this way. This is known as a straight chain molecule. This is known as a branch molecule. A branch molecule has literal branches, obviously. Straight chain, I'm pretty sure you understand what it means. Now, this surface area question is very, very specific. So I need you all to write this down. Surface area is only for straight versus branch comparison. So it's a very niche, very, very easy to identify question type. In exam, when you can clearly see a straight versus branch chain, it means you can only think of one factor to explain it, surface area. Nothing else we are going to learn, we'll talk about surface area, nothing else. Everything else is about size, and then later we talk about other factors. Really. So surface area is more applicable when you start to learn organic chem, but they can still test this in the next couple of tests. Okay, can? In other words, guys, with that said, if you have a larger surface area, what does it mean? Okay. I'm going to introduce another keyword. Okay, we have a larger surface area of contact. Okay, if you don't want to say electron cloud, you can use the word contact. Imagine this, guys. If you have a greater surface area, can you form more attractions or less attractions? More attractions, right? If you have less surface area, you can form less attractions. So think about it this way. Larger surface area of contact forms more attractions. So it's going to be stronger ID attractions. But if your branch, you have what? Let's follow the flow. Okay, good. Branch isomers have a smaller surface area of contact, which means you're going to have weaker ID interactions. Can you see this? Okay. So we're going to try a similar question, okay, which is on the, I think, 2 pages later. Okay, so to summarize this, straight chain occupies a lot of space, so the surface area is very large. Okay, a branch is a lot more compact, so it occupies smaller surface area. Can you see this? Okay, with that said, I want you guys to turn over to page 45. There is a similar question to this, and we're going to try to explain. All right? Okay, so what's going to happen here? You all see these 3 molecules. I'm going to copy on the board. Okay, the first molecule has this. Second one is this. Last one looks like that. Okay, for ease of answering this question, I want you guys to call them X, Y, and Z. So that's a bit faster. Okay, I want to bring you guys through the way to compare this question. Right? Okay, how do we do this? Which one should we talk about first? How do we classify our answer? Okay, what is the factor that we use to explain? Okay, good. Okay, why can't we use size? Okay, they all have C5H12. Okay, you can go and count out. Okay, everything is C5H12. The MR over here is like about 68, around there. Or no, sorry, 72, whatever. In other words, okay, over here, we can compare the surface area. Can we classify them first? This is a what kind of molecule? X. Okay, good. So let's talk about it first. X is a straight chain molecule. Now, if you're straight chain, what does it mean? Okay, yes, okay, you can compare that. Y and Z are both what kind of molecules? Branch. A straight chain molecule has, sorry, what do we say? Okay, can we just say the word large? In this question, we have 3 different compounds. What kind of language we use? Largest. Okay, comparative language is very important. If you write larger, they'll penalize also. That's how strict it is. Okay, 3 compounds. Let's be specific. He's the only straight chain molecule, so talk about the absolute terms. Largest surface area of contact. Or you can say he has the largest surface area of his electron cloud. Larger surface area of contact means what? Having the most surface area means the most amount of attractions, right? Okay, you can skip that part. You can just go straight to telling me strongest ID attractions. So, this question is asking you guys to rank the boiling points. What keyword do we need to use to link back to the idea of boiling points? Energy. Good. How do we say this? Strongest ID attractions require the don't say a lot, because once again you still need to use comparative language. The most energy to overcome. So whenever you're comparing 3 items, you see quite commonly, always talk about the anomaly basically. Okay, the guy who is the standout. But now we need to compare between Y and Z. How do we compare between Y and Z? Yes, they are both branch molecules. But what do you guys notice? How should we phrase our answer here? They are both branch molecules, but Ah, good. Okay, that's legit. Okay, so you must try. So who is more branch? Z. Okay, so you can say this. They are both branch, but Z is more branch than Y. Or you can say Z has more branches than Y. Also can. Now, if you have more branches, what does it mean? Okay, we talk about Z here. Z has a okay, good. Smaller. Okay, now we can renegade to the different keyword. Smaller surface area of contact, which means okay, means what? Less surface area, weaker ID attractions. Good. Okay, and then you pretty much understand the rest already. Okay, which requires less energy to overcome. Now, guys, when you revise, I highly suggest you guys to employ this method of answering long questions. You don't write down an entire fat paragraph. What's the point? You look back at it, it's just a whole chunk of words. What I do over here is kind of like an arrow system, a train of thought. Now, you don't need to follow arrows if you don't like arrows, if you think they're ugly. But what I'm trying to say is this, you must split them into small bullet points. Small segments here and there, because that is a lot more concise to look at. It's a lot more pleasant to your own eyes as well. Remember, you're coming back to this set of notes. You're revising this set of notes for yourself. Make it as nice to read as possible. Okay, so you should do this as you're writing out your explanation for this question in future. Only in exam, then you write down one fat paragraph. That's up for the examiners to see. Okay, Ken? Any questions? No? With that said, I want you all to turn back to one page before this and try to answer these two questions. They are rather easy because I already told you about the keywords earlier. Okay, so give it a try. Okay, try both questions because I realize they are pretty much the same thing. Okay, a lot of content. It seems a bit dry at the moment, but yes, okay, no choice. Right, intermolecular forces, the most important part of this chapter. Okay, so I really go through every single detail. You cannot skip any detail here. Right. Very cool because you're sitting at home. Ah,
What do you tomorrow? What do you want?
how did your interview go?
Mixed feelings.
Oh no, okay, no worries, no worries.
People said the same role because it was a role play thing. Like there were two stations, and someone role play. Then we both didn't get the role of IT, so we couldn't complete it. So it was bad. Then, and for my one, right? So the outfall was like somebody who kept bossing us around.
Wow, wait, that's a very hardcore style of interview. They call that like a I don't know what's the name. There's a name of it's an interview with what roles. Damn, I didn't know you're trying for counsel. Counsel is a pretty shit job in JC normally. Sorry? Oh, but council work is very, they always say it's very saikang. But some people enjoy it. Okay, lah, let's hope for the best, Lord. I'm ready to yeah, like, she took out the atomic structure, then she like, oh, that's not the look on the face. Okay, so I just tell you what we have gone through so far. Okay, do you remember van der Waals process last time? It's basically that, but now it's called this. Oh, you just okay, sure. Okay. Actually, it's in the Google Drive that I added you into. You can access from there, so a lot easier because mine is oh, okay. Go. Okay, I need to think of where. Oh, you didn't eat. Oh no. What's goldfish cookie? That sounds interesting.
No, but I was allergic to it.
Oh no.
You
ate it till you couldn't, meaning your throat started. Oh my god, it's even bad for you, sir. You cannot eat a lot of things. I'm wondering. No.
really going to pay. No, okay. That's okay. This is that like. Well, I think Sonia went for the my popular thing. She wrote a paragraph in her.
Yeah, sorry. Okay. Oh, you keep it. Yeah, okay. Yeah, we started from page 41, and then now we're on page like 45. Yeah, I've recorded like the first part. Okay, so you can go back and look at the details, but I can just brief you on what we have done so far. So you can think of it as this way. Okay, today we're looking at intermolecular forces, the forces between two molecules. So we are not looking at covalent bonds today. The first part of the lesson, right, I was just emphasizing on this point. We are breaking intermolecular forces. When we talk about boiling points and melting points and all that stuff, we can't break covalent bonds. That's not our focus for today. Okay, so that was the first part. As for the second part, we talked about the first type of intermolecular force. Basically, you have learned van der Waals forces in secondary school. It's a very weak, in fact, it is the weakest type of interaction. But now we have changed its name to ID attractions. As for how and why the name is like this, the one you just watched the recording for how it comes about in the first place. Okay, but for now, what you need to know, right, that it is the weakest interaction. All simple molecules have this interaction, ID interactions. Okay, you can think of it as this is the most fundamental interaction that all simple molecules must have. Of course, later we'll touch on more interactions and everything else. Okay, but no matter what, right, everyone has ID attractions inside. Okay, we look at the strength. The strength is affected by the size of the molecule. Okay, basically you look at the MR. The easiest example is this. H2 versus carbon dioxide. Carbon dioxide is a lot larger. Larger electron cloud will lead to stronger ID attractions. These three are the key words that you need to write in your question. That's it. So I'm going to go over the answer that you are doing right now. Okay, then you'll just check out. Larger MR, higher MR is all fine. Yeah. You know, this will all be in the recording. Okay, there's another factor, but this factor is not that important, so I'm not going to discuss right now. Okay, that one we just discussed. Okay, the most important factor, right, is actually what we have on page, sorry, what page is it? Page 42? 44, yes. Okay, so anyways, guys, we are given two different questions, two different comparisons. The first one is between bromine and chlorine. So when you're given two molecules, they ask you to compare melting points or boiling points. What's the factor that we look at first? Always look at the electron cloud size first, as mentioned here. Always compare size first. Who is larger? Very clearly, Br2. Okay, now you guys don't need to tell me that Br2 has a larger MR. If you want to, it's fine. But I mentioned, right, that you only need these 3 points. Br2 has a larger electron cloud, which is more easily polarized, leading to stronger ID-ID attractions. What's the final keyword you need to include? This requires more energy to overcome. In other words, you just need to repeat the same explanation for the context in this question. Okay? Then the second question, right, is the same exact thing. They are comparing hydrogen and oxygen, right? In this case, we are asking you to predict who has a higher boiling point. So what's the answer to this? O2. Because why? O2 is clearly larger. So it's a larger electron cloud. You don't need to mention the MR or anything. Larger electron cloud, more easily polarized, leading to stronger ID-ID attractions which require more energy to overcome. In other words, these 4 points are enough, right, to finish up your explanation. So it's a very simple factor to compare. Okay, and this factor, we are pretty much going to use it for the rest of the lesson as well. Okay, so 2 very simple questions. Now, I know both of them have the same explanation. But again, right, you need to write until you're very used to it. Then you don't need to refer, you don't need to copy anything. Any questions so far? Okay, so far, to summarize, we have only done the first type of interaction. It is the fundamental interaction that all simple molecules have, but it is the weakest, because fundamental means probably the weakest as well. We're going to move on to the second interaction. Okay, so turn over to page 46. We're going to change the name. Once again, I need you to write down the full name. All right. Okay, I'm going to leave this here because it's quite important. But now, right, I want you to write down the second name. That's for the second interactor. It's called permanent dipole dash permanent dipole attractions. It's the second type of intermolecular force, but in short, it's called PDPD. Now let's discuss this, right? I'm going to throw in a few facts first, and then we talk about the specifics. Number 1, it is for polar molecules. Okay, so I repeat, polar molecules have PD-PD interactions. But guys, is that correct? Do polar molecules only have PD-PD interactions? What other interactions could it have also? ID-ID, good. Okay, because guys, I mentioned all molecules have minimally ID-ID interactions. So a polar molecule has both PD-PD and ID-ID. Think of it as ID-ID as the default. Okay, whereas polar molecules is like the upsize, right? Then it has like PD-PD, it has extra stuff, add-ons. On the other hand, we just now discussed non-polar molecules. Non-polar molecules only have ID-ID interactions. So why is it that polar molecules have a permanent dipole? You look at the name and try to guess the meaning. Okay? Now, guys, later we'll answer this question. PD-PD is stronger or weaker than ID-ID. Okay, later we'll answer this. You might be able to guess the answer already. Okay, but it all makes sense. Let's recap on the polar molecule. Guys, what does a polar molecule mean? As compared to what I told you guys just now. A polar molecule is something that has an overall, not charge. What's the keyword? It's 2 words. A polar molecule has an overall dipole moment. Now remember, guys, there are some examples. HCl. HCl has a polar bond, so it's bound to have a overall dipole. We discussed this in the last lesson. We've talked about CH3Cl, right? Okay, all the CH bonds are non-polar, but there's a CCl bond which makes the thing overall polar. Okay, many more examples. Let's not go into that. What I'm trying to say is this, guys. Remember what I talked about just now? Electron cloud. Okay. The electron cloud of a polar molecule, is it evenly distributed or unevenly distributed? I give you all two options again. Evenly distributed, a very nice circle, or unevenly distributed, so a lot more onto one side. Which one? Okay, unevenly. Why? Because once again, guys, polar molecule has an overall dipole. The electrons are clearly gravitating towards one part of the molecule, right? So it has to be unevenly distributed. Have this mental image in your head from now on. I need you to write this down. Electron cloud is unevenly distributed. Compared to the non-polar molecule just now, that is evenly distributed. Right. Okay. Make sure you understand this. There's a dipole. So the electron cloud is already, what's the P word? What's the P word here? The electron cloud is already polarized. Okay, we don't use the word unevenly distributed. I like the P word more, polarized. Okay, so I'm going to draw a diagram once again, similar to what we did just now. Does it start off like this? No, right? It is unevenly distributed from the get-go. So this is how a polar molecule looks like. The electrons are gravitating towards the right, so there's an accumulation of negative charges. The left side, less electrons, so there's an overall positive charge. The molecule on this right is also a polar molecule, so you have less electrons on the left, more electrons on the right. Can you all see, right, from the start, it already has interactions, negative, positive. This right here is your permanent dipole interactions. Can you all see why it's called permanent? Because guys, remember what a non-polar molecule is? Does it start off like that? A non-polar molecule starts off evenly distributed for its electron cloud. But then what happens? Can you all repeat to me what happened just now? Electrons are always moving, right? So at any random moment in time, at any instance, it's just gonna get polarized like this. Then you will form your ID interactions. Now, what's the difference? I want you to think of it this way. This is permanent. Is that forever? But is this permanent? This is fleeting, temporary. Make sense? It only created at that moment. So which one do you think is stronger? Something that's permanent or something that's temporary? Clearly permanent. Okay? So, diagram I'm not very interested here. Someone can talk. Because there's a dipole moment, it's already unevenly distributed from the get-go. So PD is stronger than ID. Okay? I don't want to just tell you guys it's stronger and then just accept it. No, no such thing. You can accept it, but what does it mean? Okay, this is what it means. Okay, the word permanent is already a clue itself. Okay, so get this, polar molecules have this additional interaction. Not just a PD, guys. It has both. Okay, now, because we understand what it is already, I want to very, very briefly touch on the factors. The factors really not important. In fact, it's just one factor. For PD interactions, the factor is literally its electronegativity difference. So I can give you a very simple example. HCl versus HBr. Now, which one has a greater electronegativity difference? Wait, no. Okay, remember, what are the top 3 most electronegative elements? Phon. Guys, the closer you are to Phon in the periodic table, the more electronegative you are. Does that make sense? So you look at the periodic table, FON is literally on the top right. Cl is here, Br is here. So who is more electronegative? Who is closer to F? Chlorine. So if chlorine is more electronegative, that means the HCl bond is more what? More polar. Now, if you're more polar, that means the PD interactions are going to be stronger, right? Okay, it's very intuitive. More polar, stronger PD. And that's literally that's literally it, guys. Okay, nothing much for me to discuss here. There are no other factors. It's just like that. Yeah, I think this is the most intuitive thing you can think of already, right? But I need to clarify one thing. And this is something I need you all to write down right now. Okay? I did mention, guys, no matter what kind of molecules they give you, what is the first thing you must always compare? still on the board. I never erased for a reason. You must always compare electron cloud size first. Now, I don't care whether it is non-polar or polar. You must compare size first. Why does this make sense? Guys, because I already mentioned, electron cloud size just now we used to compare ID attractions. But the fact of the matter is this. All molecules, no matter polar or non-polar, have ID. So because of that, it only makes logical sense to compare electron cloud size first, because it's the fundamental interaction of every simple molecule. But can I ask you, in what situation can you not compare electron cloud size? When the MR is similar, like maybe not 2 and 44, maybe 42 and 44. Then you compare other factors. So, in other words, if the electron cloud size is similar, so I write this if similar MR, then we shall now look at the other types of intermolecular forces. Later we will see what this means. Basically, now we are allowed to explore other types such as PD-PD, which could be stronger than ID-ID. This framework, guys, is very important when you are comparing any two molecules. There's a practice on the next page. Okay, we're just going to apply this immediately. Okay. So pay attention to this. Okay, there are many misconceptions that come out with this. A lot of people never compare electron cloud size first, then all the questions wrong. Okay, I will give you guys a negative example in the next page. Okay, erase this a bit. Okay, I need to erase this. No space. Okay, just very quickly, once you're done, right? Turn over to this next page and then just read through this question. Looks very simple actually. Okay, and this question will allow me to prove a few points when it comes to chem bonding questions. So pay close attention to this page, right? So 3 molecules. What's the boiling points? 12, 35, okay, about there. Okay, so they gave you this set of data. Your job is to explain why. Why is it like that? Why does it increase down this thing? Right? Okay, how do we explain this? Okay, first of all, guys, let me show you how a wrong answer would be. And don't think that, I'll never think of this wrong answer, because you might fall into this trap. Okay? These 3 molecules, polar or non-polar? Polar, right? Okay, great. Polar molecules, what interaction does it have? Okay. Okay, it's PD and ID, okay? But because all molecules have ID, okay, this is what a wrong answer would look like. Oh, polar, PD. Not wrong one, right? PD. Okay, so for PD, guys, what was the factor again? PD, the factor was to compare the electronegativity difference. Now, guys, you look at the bonds, the bond that I'm really concerned with is CCl, CBr, and Ci, right? Who is the most polar? Okay, who's the most polar of all of them? Okay, good. CCl is the most polar. The least polar is obviously Ci. It's the furthest from chlorine. So if you're the most polar, that means what? Strongest PD. Least polar means weakest PD. Hey guys, at this point in time, am I wrong in any aspect? I'm correct, right? It's not wrong that these are polar. So they have PD, I'm not wrong. I look at the factor, also not wrong. But can I use this answer as my answer? This. Why not? Okay, I mentioned all that just now, right? But look, it doesn't fit the data set. It would have been the complete opposite, right? Now, this is what chem bonding is about, guys. Okay, in chem bonding, you are rarely required to predict the boiling points. In fact, as I mentioned, the theme of today's lesson is to explain things that we see in real life. Physical properties. Why are the boiling points like this? We seek to find the correct explanation. Meaning to say, guys, most questions that you see in exam, they will give you the boiling points. Your job is to find the correct explanation to these observations. Okay, that's what science is about. Okay, is to find correct answers to what you see. So it's very clear that this is the wrong answer. Even though the logic, the thought process is correct, it doesn't allow us to arrive there. So now let's follow whatever I taught you guys. What's the first thing you must always compare? Emma, I told you already, electron cloud size first. What happens to the electron cloud size when you go down the route? The electron cloud size increases, right? Okay, Cl to Br to I becomes bigger and bigger. When electron cloud size increases, it becomes more easily polarized. If you're more easily polarized, that means what? The ID becomes stronger and stronger, requiring more energy. It is the same exact explanation as just now. Does this fit the data? Yes, so use this. It's quite clear the size increases. You don't even need to compare the type of interaction. There's no need for you to mention PD in the first place, right? Again, now guys, ID is still present in these molecules. Don't get confused by that. It's still a valid explanation. So that's your answer. Now, I want you to go and write down the negative answer also, the wrong answer that I explained just now. Okay. If you want me, if you don't copy that, I'm going to write it down again. Okay, the wrong explanation was this. Let me write in black, huh? Right? Okay, the polar, so you all think of PD. Then you all say that the bonds become more polar and all that. Okay, so this is the wrong thought process.
For Cl, it has
Yep.
the smallest electron content.
Correct. Okay, you realize the rest of the molecule is the same, right? So you don't really need to look at this. You just have to look at the halogen. Okay, so weakest PP. Okay, then go and write all this, write the wrong version out also. And I need you guys to go and say that this does not fit the question. It does not answer the question. So please never fall into this trap. Correct thought process, but wrong application. Okay? So definitely try more examples later. Okay, but talk about the third one after this. Okay, there's a lot of content. Okay, if you guys need a break, just feel free to go toilet or whatever. Okay, I'll go over maybe a little bit of the next interaction, right? Then we take a short break. Okay, if not, it's a bit too overwhelming. Any questions so far? Okay, so to summarize, we have done two interactions, ID-ID and PD-PD. Every simple molecule has ID-ID. PD-PD is just an additional interaction for polar molecules. But now let's look at the third interaction. I thought we only learned polar and non-polar. How come got one third interaction, right? Okay, so let's take a look. Right, so the third interaction, very short name. We're going to leave this here first. Okay, the third guy is called hydrogen bonding. Now, I don't like the name of this guy. You all know why I don't like the guy's name? Why do I not like this name? Why is it a very ambiguous name? Is it a covalent bond? Guys, I mentioned, are we talking about covalent bonds today? No, okay, this is an intermolecular force, not a covalent bond. That's why I don't like this name. Why does it have a word bonding inside? I don't know. Don't ask me. Yeah, okay, unfortunately, it's like that. So we have to accept it. Okay, what's hydrogen bonding? Let me just give you an analogy. It is for polar molecules, yes. Okay. I thought PDP is for polar molecules. But no, it is for the top 3 elite club. Who are the top 3 most electronegative atoms? 4. Guys, FON are like the cream of the crop. It's like your school, the most ups girl or whatever, okay? He's in a league of his own. These 3 people, FON, are in a league of its own. That's why there's a very special name for them. Hydrogen bonding. Now guys, okay? Another fact is this, hydrogen bonding is the strongest out of the 3 intermolecular forces that we've learned so far. It's stronger than PD-PD, and PD-PD is stronger than ID-ID. So you should know this ranking system already by now. We're just getting stronger and stronger. But guys, think of it this way. If you want to enter the very exclusive club, do you think it's very easy? No. You need to have very strict criteria to enter a very exclusive club, right? So here, there's some things that we need to understand. The criteria to exist, to have hydrogen bonding, is very stringent. Okay, and I'm going to introduce this idea. Okay, follow me on this. I'm going to cover the criteria. Right? This one you all must know. For hydrogen bonding to exist, you must minimally have how many molecules? Can you have one molecule to have? No, right? Okay, it's intermolecular, between molecules. So I'm going to call this molecule 1 and molecule 2. You can imagine this in your head, right? Okay, I have intermolecular forces. So guys, in order to form one hydrogen bond, each molecule must fulfill some sort of specific criteria. Now, I'll tell you the criteria straight up first, right? The first molecule must have hydrogen bonded to F, hydrogen bonded to O, or hydrogen bonded to N. Not all three, either one can already. Then can you all see FON, exclusive club? There must be hydrogen, if not, why is it called hydrogen bonding? Very easy to remember, right? Yeah. How about the second molecule? The other molecule must also have FON. You can think of it as this way. FON is like the key to enter this club. Is the password. Okay? FON must contain a lone pair of electrons, which they usually do lah. Right? Later you look at examples that I'll show you. Now there's one thing I really need to clarify for this. Okay, but you'll write down first. Okay, write down whatever you need to. Now, I'm gonna write down a thing. Okay, I can't really phrase it very properly here, but you'll just see what I mean. Each molecule just needs to fulfill one criteria each. Okay, I repeat the word each twice because it's referring to different things. I'm not repeating for fun here. Yeah, okay. To put it simply, guys, molecule 1 just needs to fulfill criteria 1. Then that means the second guy must fulfill criteria number 2. What a lot of people think is this, molecule 1 and molecule 2 must fulfill both criteria each to form the hydrogen bond. No. One each, okay, one criteria each fulfills the hydrogen bonding criteria already. Okay, if you look at what it means, okay, in a bit. Okay, but I hope you understand what this statement means now. Okay, never mind. Okay, we take a look at the examples. Take a look at the box. We're going to draw a diagram. All right. Now, this diagram, guys, we check water first. I want you all to ask yourself this question. Can water have hydrogen bonds? Yeah, of course, one molecule is not enough to see that one, right? I always want to see at least 2 molecules being drawn. Okay, let me draw another water molecule here. Okay, guys, the first molecule of water, does it fulfill the first criteria? Yes, okay, yes, HO bond, right? If this guy fulfills criteria 1, this guy must fulfill criteria 2. He doesn't need to fulfill 1. I know he does, but he doesn't need to. Does he fulfill criteria 2? Yes. He has an oxygen with a lone pair. So this is what we're going to do now. Okay, yes, he can undergo hydrogen bonds, right? But write down the 3 criteria in your diagram. If any criteria is missing, they will penalize. Yes. Sure. If you want this to be M1, this one can be M2 also. Sure, up to you. Yeah. But later, right, I'll give you an example which isn't that flexible. This is very flexible. Okay, it just so happens, guys, that water fulfills both criteria 1 and criteria 2, right? It can lah. Later you'll see another example. Okay, anyways. First one is I need to see partial charges because, guys, this is all about polar molecules, right? Okay, polar molecules must have partial charges. Second criteria, I need to see the lone pair of electrons drawn very carefully. Like basically, I need to be drawn. Okay, the last one is very simple. Label the hydrogen bond. Okay, so follow me on this. Label all the partial charges. Partial plus, partial minus. Okay, oxygen is partial 1. Partial minus. Hydrogen is. Okay, you must do the same thing for the other guy as well. So partial minus, partial plus. Guys, take note also. The partial charges, I need you to draw it in pairs. What does that mean? Here I must see 2, here I must also see 2. Okay, what a lot of people will do, they just draw one each. I also don't know why. They must come in pairs. Okay, lone pair of electrons is on where, by the way? Oh, yes, but which O? Yeah, is it this O or this O? Okay, guys, you see, the lone pair is in the second criteria, so it must be this second molecule here. Does that make sense? Because draw here also no point. So I want to see the lone pair of oxygen being drawn. Because, guys, the lone pair is involved in the hydrogen bonding process. Now, how many lone pairs does oxygen have? Ooh. You remember your VSEPR we did last lesson? Oxygen has 6 valence, right? So 6 is 1, 2, 3, 4. Actually, you have another 2 more, 5, 6. But you just need to draw one, it's fine. You want to draw both, also go ahead. Okay, finally, guys, where do you think the hydrogen bond is being formed? Between what and what? Anything attracting each other? And then O is minus, H is plus, right? Okay. Do this. That is the hydrogen bond. Please label it. Must label. That right there is a full diagram of a hydrogen bonding of water. Okay? Any issues with this? We're going to practice more of this, more examples. Okay, the next page, the example very good. Okay, so must highlight this page also. Okay, so come. If no issues with that, can you turn over to this next page to really see whether you all understand this? Take a look at part A. Try to answer this question. Okay, if you want to help yourself see, make sure you draw 2 of those molecules. And you're going to label your M1, M2 if possible. Give you all maybe 2 minutes to try this. Right? Use. You can't really know it. You can't really know. Oh, sorry. Yeah, cable. Oh, really? Oh, no. Your temperate the lab got aircon on. So what do you do with temperate? Titrate. Oh, yeah, easy experiment. Huh? Titration you're doing for like a few weeks. Why? Then you just titrate once and finish. Oh, this actually they go quite slow for titration. Interesting. Okay, guys, we answer part A, can or not? Why not? Yeah, okay, good. That is the explanation. Okay, see, so this is how you should do it. You look at one molecule here. Which criteria does he fulfill? 1 or 2? 2, because he has a lone pair. In fact, 2 of it on there. If this guy fulfills criteria 2, this guy must fulfill criteria 1. Does he fulfill criteria 1? No. Okay, so the idea is this. The keyword here is with itself. So you draw 2 of the same guys. The explanation is very simple. There is no H bonded to O in methanol. This guy is called methanol. Okay. A lot of the times they won't ask you guys to explain. More often than not, they will just ask you to determine whether can or cannot. Hey guys, then this is very important. If you can't undergo hydrogen bonding with itself, then what interactions does it have? Cannot be nothing, right? Okay, go write this down. Cannot undergo hydrogen bonding. So methanol has what? Methanol is held together by. Think about it. What interactions? We learned 3 today. IDID, PD, or not hydrogen bonds lah. So you only have 2 options. Okay, which one? Okay. Okay, so all molecules have IDID, right? Okay, so that one is like okay. But does it only have IDID? No, because this is a polar molecule. CO is polar. So since this guy is a polar molecule, generally to answer this question, you just tell me it's held together by PD attractions. You don't need to say held together by PD and IDID. Because at some point, guys, IDID is kind of implied in all molecules, right? Even if you don't say it, you're expected to kind of like know that everything has IDID. So it's a useless thing to tell me that it's IDID fully. Okay, yes, PD. Okay, that's what you should answer with this question. Okay, he's not part of the special club because he never fulfilled the criteria to enter the special club. So he's only just a normie. Yes. Yeah, you have a lone pair. But the other molecule must also play his part, right? If this guy has a lone pair, he fulfills criteria 2. That means this guy must fulfill criteria 1. Okay, because water is a lot more flexible. If you look at water, right, it has both criteria 1 and criteria 2 on just one molecule. So if it has both criteria here, right, that means if you draw another water molecule, it can go both ways. If this guy is molecule 1, this guy can be molecule 2. But this guy can be molecule 2 and this guy can be molecule 1 as well. This guy is not as flexible because he doesn't have the H bonded to both. So that's the idea. Okay, that's why this gets a bit confusing sometimes. He does not fulfill criteria 1. Does it make sense? Okay, makes sense. Huh? Hey, you all can try part B. So, right? Okay, that's why when your school goes through like water, right? Water is like the most common example. Right. A lot of people start to get the idea that you need to fulfill both criteria. Because it so happens that water exhibits both. But it doesn't have to. And methanol illustrates that. Okay. Okay, first of all, you must determine whether you can form hydrogen bonds with water in the first place. Okay, if cannot, that means you don't need draw. Yeah, you just not bonding, I don't use that word. Okay. Interaction means IMFA, yes. Okay. So they say identify what interaction. So ideally PD, hydrogen bonding, 3 only. Okay. Yeah, go ahead, go ahead. Yeah, after this, you finish his break already. Yeah. Just try your answer. Oh no. Okay, the position of the lone pair must be inside the bond. Yeah, so it is like kind of outside the bond. So maybe the partial charge will like kind of shift it out a bit. Yeah, okay, good. Okay. Yes. Yo, what are you here? Which one? Okay, no. They can form hydrogen bonds with themselves. Okay, the reason for that, right, is because now let's draw a water molecule over here. Okay, so the thing is, we start the whole process. They must fulfill these 2 criteria, 1 each. Methanol, which criteria does he fulfill? Criteria 1 or 2? Methanol fulfills 2, right? He has an oxygen with a lone pair. If this guy fulfills criteria 2, water must fulfill criteria 1. Does it fulfill criteria 1? Yes, it has a HO bond. Now that each one of them fulfills 1 criteria each, right? The hydrogen bond can exist. So the answer is hydrogen bonding. Okay? Okay, your partial charge here, right? It's not on H. It's on C. CO ma. Yeah. It doesn't work. Yeah, maybe it's a careless mistake. Yeah, very careless. Right? Okay. Anyways, yeah. I'm just drawing the diagram. Sorry? I mean everything is ID, but you don't need to mention it. Okay, it's already implied that everything has it. Yeah. Okay, he's part of the special club hydrogen bonding. So it doesn't have PD between these 2. Okay, you are one or the other. Are you special enough to be the hydrogen bonding or normie? A normie means you are just a PD interactions. Okay, interactions wise, guys, let me draw one answer and y'all tell me whether this is correct. Okay. Okay, let me show you guys one answer that a lot of students tend to give me. Okay, so O and H, very nice, hydrogen bonding. Right? Okay, correct. Then I put my partial charge, I label this hydrogen bonding, and then it's partial negative. Yeah, correct. What's wrong with this? There are many things wrong with this. Now, the reason why a lot of answers come out with this, right, is because you all see an O and a H very conveniently, just go and put them together. What is wrong with this diagram? Okay, don't need to draw this out. Okay, you all just need to tell me what's wrong with this. Okay, so it's very clearly that you're not going with your criteria, right? Okay, at the same time, guys, does CH have polarities, have partial charges? No, okay, this is completely wrong. Okay, so the reason why answers like this tend to come out is because you all don't understand the criteria enough. I told you all the criteria already. Okay, so you must follow the M1, M2 criteria as closely as possible. Here is M2, so the lone pair on this oxygen must be involved in the hydrogen bonding. Here is M1, so I need to see the OH bond being involved in the hydrogen bonding as well. Okay, let's draw the other H. Label in all the other stuff. Okay, lone pairs inside. Partial charges are here and here. Label hydrogen bond. Okay, style the whole thing. Don't just write that H bond. I don't know whether a teacher will accept that. Okay. You take a break first, right? This diagram here usually 2 marks. Okay. CH, the electronegativity difference is very, very small. So there's no partial charges. Considered non-polar. That's why you don't draw anything here. Hello? Okay. Okay. Thanks. What's the interview for? Like, it's like what position? Oh wow, so intense.
No, I went to the
All right, guys, let's continue. So, the most important takeaway of today, right, is stress is dessert spelled back. Okay, so stress is dessert spelled backwards. So, yeah, don't be so stressed. Okay, you can't even eat desserts. Yes, desserts. Eat more desserts now. Okay, anyways, I'm going to move on to factors. Wait, what? Your lunch was a watermelon. You know, watermelon is not food, right? It's basically drinking water. It's actually like, doesn't feel anything. Alright. Okay, guys, let's continue here. Okay, you can just take a look. Now, the next page, we're going to look at factors. The factors for hydrogen bonding, right? Quite a lot. Like, that's why we spend the rest of the lesson covering this and we are done already. Okay, anyways, the first thing, right, is the easiest factor. Electronegativity difference. Now, the idea is this, guys. Remember, this one, there's not much to it because hydrogen bonding is a very special club of bonds. Okay, you have HF, you have HO, and you have HN. In fact, right, there are only 3 bonds for you to compare electronegativity difference. Guys, which one is the most polar out of the 3? HF, right? Okay, so if you're the most polar, you will have your hydrogen bonds are bound to be the strongest. Okay, compared to the HN, that's the least polar. So it's the weakest hydrogen bonds. Now this one's very simple, nothing much for me to say, right? Now you would think that this is the only factor that affects hydrogen bonding, since there are only 3 possible bonds, right, in hydrogen bonding. But unfortunately, right, this one small little factor here doesn't explain everything. And we're going to use an example to highlight this. All right, guys. I want you to tell me, right, your expectation for this question. Okay? Based on just this one factor that I've taught you guys so far, I want you guys to rank these 3 compounds in terms of increasing boiling points. Okay? NH3, H2O, and HF. Guys, can you tell me who is the lowest boiling point? Okay, NH3 followed by H2O followed by. Okay, good. Now you can come up with this ranking because you are basing it off only one factor. However, guys, this is not actually true in real life. When we observe the boiling points in real life, right, it's actually NH3, HF, then the highest boiling point, surprisingly, is H2O. Now, what is going on over here? Okay, so what we're going to do here, right, is I'm going to answer the question on page 51. This example on page 51 will help us highlight 2 factors. Okay, so you can basically turn over to the next page and write everything down. Okay, there's a lot of space. Okay, so jot down whatever that's not. Okay, I'm not going to jot down the answer yet. Okay, but jot down every single other thing as well. Okay, guys, from this observation, is one factor enough? Clearly not enough, right? It's not comprehensive enough. That's why we have to look at other factors. Okay, before that, guys, you compare these 2. Can we use electronegativity difference to explain this? Does it make sense? Wait, it does. Because HN is more polar than NH3, it does make sense. Okay, so for here, we're going to use electronegativity difference to address the first point. However, can we recycle the same thing for water? Clearly not. So what I want you all to write is this. You can use electronegativity difference for the first set of comparison, but you can't use this to explain water. In other words, we have you have to include other factors as well, which is what brings me to the second point. The next factor we're going to use to seek to explain this is called extensiveness. The extensiveness of hydrogen bonding. More extensive versus less extensive. Okay? So let's explore what on earth is extensiveness. Basically, it is the number of hydrogen bonds you can form per molecule. Go write this down. It's the number of hydrogen bonds formed per molecule. Okay? Let's understand what this means. If one molecule can form only one hydrogen bond, do you think that's very extensive? Not really, right? Okay, if one molecule can somehow form 1,000 hydrogen bonds with just one molecule, is that extensive? That's very extensive. Okay, so how do we measure this? Okay, let's take a look. How do we determine how many hydrogen bonds a molecule can form? Let's look at all 3 structures. Okay, I need you to take this down also. NH3 looks like this, if you all remember the shape and all that. But how do you form one hydrogen bond? I need you to remember this. In order to form one hydrogen bond, how many criteria do you all need to fulfill? There were 2 criteria, right? Now, can you all tell me the 2 criteria again? What's the first criteria? KH bonded to F or O or N. What's the second criteria? Lone pair of electrons on F, O or N. Right? Now the idea is this, guys. You must have one of each criteria. So come, Let's list down for NH3, how many of criteria 1 are there? How many NH bonds are there? There are 3 NH bonds, right? So there are 3 NH bonds. That's for the first criteria. How many lone pairs are there on N in NH3? How many? 2 pairs? No, just 1. Yes. Okay. So remember, nitrogen has 5 valence, 3 of which used in bonding. So the other 2 is not used in bonding. That's a lone pair. Now remember, guys, a lone pair is not involved in bonding. That makes sense, right? Okay, so guys, if you have 1 lone pair and 3 NH bonds, can y'all tell me how many hydrogen bonds can this guy form? Careful, think about it. You need 1 each to only form 1 hydrogen bond. So how many can you form here? Just 1, right? You can think of it as this way, guys. The lone pair is like a limiting factor. Okay, so there's only 1 hydrogen bond formed per ammonia molecule. You can do the same thing for HF and water as well. Okay, so let's draw all the structures. Repeat the same thing. Okay, HF. Guys, for HF, how many of criteria 1 is there? Okay, very clearly, I only have 1 HF bond, right? How many lone pairs are there on F? 630, but 7 out of 12 got 12. Oh, 630. That's in the scanner. Okay, guys. 3 lone pairs because fluorine has 7 valence, so only 1 of it used in bonding, the other 6 not doing anything, right? So 3 lone pairs on F. In total, guys, how many hydrogen bonds can you form with this set of criteria? 1. And before I move on, guys, can we use extensiveness to compare this first set over here? Clearly not. Both of them have the same extensiveness. It is not viable. That's why we need to choose our factors wisely. Okay? You can very clearly see from this over here, you must choose the correct factor to explain what you observe in real life. In other words, guys, let's now move on to water. For water, how many OH bonds are there? 2, very obvious. How many lone pairs are there on oxygen? 2. Oxygen has 6, 2 of which used in bonding, so the remaining 4 not doing anything, lone pair. Guys, how many hydrogen bonds can this guy form per molecule? 2. Now imagine this, guys. What does it mean by water forming 2 hydrogen bonds? 1 water can form 2 hydrogen bonds with more water. Then this one become 4. 1, 2, 4, 8, 16. It multiplies, right? It's quite exponential. Whereas for HF and NH3 is just 1, 1, 1, 1. Is that very extensive? 1, 1, 1, 1. No. You see, just having 2 hydrogen bonds itself, right, makes it super extensive. And because of that, guys, we can now finally touch on the explanation for this entire question. Okay, kind of run out of space. Okay, so you all copy these 3 diagrams out first. Okay, then I erase this up. Okay, now let's write down the full explanation. This whole thing, right, can carry up to 3 marks. And if you understand your factors well, right, 10-1. Okay, come, let's take a look. Explain the first one, the first set. Okay, the first one very easy. Okay, you just need to tell me HF is more what? More polar than NH3 or than HN. Sorry, we're talking about the bond only. Hence, HF has what? Being more polar leads to stronger hydrogen bonds. Remember, let's go straight to the point. We don't have much time to explain this in exam. Okay, HF has stronger hydrogen bonds than NH3. What's next? Which requires? Which requires more energy to overcome. Now, at this point, right, want to highlight, right, that your answering format is usually the same for this entire chapter. Not just for IMFA, but even for structure and bonding. Your answering format is like this. You tell me the factor, then next you go to strength, and finally, energy. So look at my answer, my format here. The factor, the strength, the energy. Three things. Follow this and you are set. Don't need to write too much. Now let's repeat the same thing for extensiveness of water. Okay?
Okay.
Okay. So you can see this, immediately I go straight to the point. I think some of you guys will tell me this. Water can form 2 hydrogen bonds per molecule. HF and NH3 form 2 hydrogen bonds per molecule. Then you are wasting a lot of time. Okay, what you need to do here is just go straight to comparing. You are comparing, right? So just go tell me it forms more hydrogen bonds per molecule. You must do this. Don't forget the word per molecule inside. If you can form more hydrogen bonds per molecule, it means water has more one. What's the factor? The key word here is extensiveness, right? It has more extensive hydrogen bonds, okay, than HF or NH3, which are stronger and require more energy to overcome. You see how I make my answer very concise?
Okay.
Some of you guys will blow this answer out of proportion, meaning to say, more extensive hydrogen bonds, stronger, and more extensive means stronger hydrogen bonds. They repeat the word hydrogen bonds twice. Okay, this is how you shorten your answer. Okay, I tell you this from the get-go, right? Okay, then know you know. Okay, follow the same thing, guys. Factor, strength, energy, right there. Okay.
Oh, for your thing, right? The thing was that
I didn't talk.
okay, only the first down will okay, we say this will be big one. Everything else I got there.
Okay.
Okay, now.
Whole thing here is 3 marks.
Okay.
Okay. They can allocate. This one depends on the answer key. Okay, they might give more marks for extensiveness. Less marks for the electronegativity because that's very easy. Okay, Ken? There's one more thing we need to go through and then we are done for today. Okay, so we started like 10 minutes late. Okay, just nice. Okay, about 10 more minutes. Okay. Okay, if you all take a look at page 52, I will be explaining question 3. That one, right? We will use the third factor to discuss. Question 2, maybe you all can do yourself at home first. Okay, that one not too hard. Okay, we cover it. 2 factors done. Let's look at the last one. Okay, any questions so far? Okay, you can think of any questions you can have. Right.
Yeah, able to make sense of any other. Very, very good.
Okay, last one.
So ionic bonding, right? You need to be able to identify ways of
okay, so let's take a look. The last one, right, is called intramolecular hydrogen bonding. Okay, let's unpack some simple terms first. What is intramolecular? Okay, it's between. The entire time we were discussing intermolecular forces. Inter means what? Between molecules. Whereas now intra means sorry. Not between atoms, but molecular. So we don't use the word atoms. Still molecules, but within molecules. You can think of it as this way: inter-school competitions versus intra-school competitions. Inter-school, that means RI play with some other school. Okay, but intra means you play within like the school itself, okay, between classes or whatever. Okay, now what is this? You can form hydrogen bonds within the same molecule, and the structure we're going to use, right, to explain is on page 52. Now, this concept is a little bit harder because it's more towards organic. Okay, but there's a chance you can test also. Okay, but never mind. Quite simple. The question that we are looking at is this.
Well, what about
The structure in the notes is very similar, lah. Okay, but all I need you all to do, right? Okay, there's no names for these two guys. So to make things easier for you all call this guy X and call this guy Y. Okay, I'm going to refer to them X and Y from now on. This is something you can do yourself also. Okay, but anyways, you look at X, you look at Y. Can you tell me first, if they ask you to compare melting points, what's the first thing you should consider? No matter what kind of two structures they give you, you must always consider their electron cloud size. Yes, exactly. You look at the MR of these two guys, same or different? Same. What's the difference between these two structures then? Okay, you can see the position of the things are different, right? Okay, so we can't compare electron cloud size. So what do we do? Okay, no surface area. I remember saying, okay, that one's only for straight versus branch. It's not an idea. Okay, I cover this again. Electron cloud size, if cannot compare, like in this scenario, we go towards the types of intermolecular forces. What are the different types? Okay, can list down for me what are all the types that we've learned today? ID, what else? PD, and hydrogen bonding. Okay, quite clearly, we are talking about hydrogen bonds here, right? But you notice, both of them, they are the exact same molecule, so they can still form hydrogen bonds with itself, correct? That's the OH. That's how you can form hydrogen bonds. But the difference is, of course, the factor. Who do you think can form hydrogen bonds within the molecule? X or Y? Look at the positioning of the things. Y. Okay, Y. Yeah, Y. You see they are close enough, right? They're situated next to each other. What's going to happen is this. This H can form hydrogen bonds with this O. I'm not interested in the full diagram, so I just draw the line only. But can this guy form hydrogen bonds with itself? It's very far, right? So this one cannot. This guy here, Y, has the presence of intramolecular hydrogen bonds. Yes. How about X? They're close enough to each other. They also fulfills the two criteria. Okay, this guy is a lone pair. This guy has OH, so they can form with each other. Two criteria. Okay. Okay, now notice guys. Okay, this part here must follow very carefully. X, what kind of hydrogen bonds does it form? Intra or inter? Intermolecular, right, guys? If I were to place another molecule of X, they can form hydrogen bonds with each other. So right here, intermolecular hydrogen bonding. I ask you all the same question. Can Y have intermolecular hydrogen bonding? If I put another Y over here, can or not? Actually, it can also. What I need you all to acknowledge is this. On top of the typical intermolecular hydrogen bonding, this guy has additional intramolecular hydrogen bonding. Write this down. He doesn't only have intramolecular, he also has intermolecular. It's the same. Okay, it also has whatever it has before. How does this affect your strength? Okay, come. I'm gonna write down the answer to the first part first, then I explain to you all. Follow carefully. My choice of words here very, very careful.
Sorry, 3 more, right? So then we have 1 here, 1 here, 1 here. From what you learned in the topic, you notice that right? So we have here. So this is -3, there is -3. Okay, then also not need to right? So group agent, what I need to figure out the number of electrons.
Pause here, pause here.
Does it already have to go back?
A few things to highlight. It has intramolecular hydrogen bonds, but it causes its intermolecular hydrogen bonds to be less extensive. A few things guys. Number one, why am I coming back to intermolecular force? Because look at the theme of today's lesson. To explain the physical properties, I talk about intermolecular, not intramolecular. I say one more time. Intermolecular explains the physical properties. So I still have to link back to its intermolecular forces. But what happens here is the presence of intramolecular hydrogen bonding will cause the intermolecular to be less extensive. In other words, guys, this is a cause and effect scenario. Intra, cause, inter to be less extensive. Why is this so important? Because the misconception a lot of people have is this. Y has intra, X has inter, and Y and intra is less extensive than inter. This is wrong. It's not an intra versus inter scenario because both of them eventually have intermolecular forces. But this guy has additional presence of intramolecular, which will undermine its intermolecular forces of attractions. Okay, because if you form within yourself, you can't really form outside as much. Does that make sense? Okay, put it in simple English. You form inside, you form less outside. Okay, you form more inside, your outside cannot form as much. You're not as you can't branch out as far as you can. Okay, that's all you need to know for this. Never ever tell me it's not okay. So it's an A result in B scenario. Not an A versus B scenario. Never ever do this. This is very, very problematic in a lot of answers. Okay, so look at this. And then now, since I use the word cause, okay, then the rest are the same. Okay, Y has weaker hydrogen bonds, which require less energy to overcome. You will see this scenario more in organic chem. So I doubt, right, they will test this early into the year. But it's still a factor that's taught in chem bonding because it's still about physical properties. Okay. So in other words, okay, the other keywords, yes, I talked about that before. So Y actually has a lower melting point compared to X. The main issue is once again people thinking it's intra versus inter, which is what even I thought last time. When I was a student, right? No one clarified this with me. Okay, they just said like that. Then I thought it's a 1 versus 2 scenario. Okay, you all must understand at the end of the day, right? The theme of today's lesson is all about intermolecular helps to explain physical properties. So you always must link your answer back to intermolecular forces. Okay, with this? Yes. Yeah.
Affect the number of bonds that you can form outside, like the interbonding. What will it affect the strength of the bond?
Okay, extensiveness, right? You must understand this intermolecular, right? It's not being undermined by any intramolecular. So this guy can form a wide network of hydrogen bonding. So you can think of it as this way. X, right? If the network is very, okay, I can't draw a network, but it's very, very widespread. If the network is very widespread, you need a lot of energy to break it. Super strong network. You can think of it as an extrovert. An extrovert likes to make a lot of friends. So he has a strong social circle. Extensive. The idea is always linking back to extensiveness. Why is like an introvert? An introvert likes to keep to himself, doesn't really like to make a lot of friends. His social circle is not as strong, not as extensive. If you have less network, right? Okay, you definitely need less energy to break. That's why it can be talked about, it can be linked to strength. The misconception, I can talk about one more thing. Some of you guys tell me, oh, you have additional intra, right? If this is additional, shouldn't you be stronger? Because you need to break more things, right? No. It just undermines the inter. It actually affects. That's why I say it's a cause and effect scenario. One thing affects the other. It's not the add-on. Okay, maybe this is not a good plus. I should use the plus sign. Intra will affect the inter. Okay? It's not really a plus sign. Maybe I should stop using a plus sign. Okay. So it's not on top of the inter, it undermines the intermolecular forces.
Okay, so take a look at it.
Okay, it's not an easy concept to digest, yes, I know. Okay, and because of that, right, that's why we need 5 lessons to cover. I can't cover solubility. Okay, because that's how much detail we need to go into. Okay, the question on top, I covered all the things required to do it already. So go and try that yourself. Next lesson I can go through. Okay, with that said, that's all for today. Okay, what I need you guys to do before the next lesson. Next lesson, a lot of tutorial questions. And even then, I'll give you a lot of homework. Chem bonding very important. So, okay, what we're gonna do, right? Next lesson before you all come is read through everything. Not just IMFA. Okay, still got more stuff. Okay, try to review it before the next lesson. If not the tutorial, next lesson you come down, then you struggle a little bit. Okay? If there are no questions,